This video in the Resources on Proof series is a follow-on from the How to Start a Proof video. Now in that video we gave a strategy for how to approach to prove something if you weren't sure on how to get the idea behind it. In this video we're going to be looking at the examples method and we're going to be applying it to a particular statement. I'm going to be going over all the steps in this process, so if you've already watched the syntactic method video, please feel free to skip to the examples section that you've not seen before, which is the time of which is in the description of the video. So in the comprehension stage, the goal is to understand what the theorem is saying and to analyse its logical structure. So let's look at let's analyse a particular theorem. This theorem says that every convergent sequence of real numbers is bounded. So let's understand the objects in that theorem. The objects are quite clearly sequences of real numbers, which are for every natural number we have a real number. We're assuming that that sequence is convergent and we're concluding that it's bounded. So this has a very simple logical structure of convergent implies bounded. So let's write out all the definitions involved. A sequence of real numbers is, for every natural number, a real number, an. Convergent means that there is some number a, such that for every epsilon greater than 0, there is a natural number big N, such that if little n is greater than or equal to big N, then the terms in our sequence are only epsilon away from little a. Bounded is that there are two numbers, L and U, such that every term in the sequence is between L and U. The next stage is reworking the definitions, and in this case we don't have much to go on. If we rewrite the definition of bounded in this way, we can see that we can perhaps have a slightly easier time not having to define both an L and a U, but the two seem pretty strange. One's different. One's talking about a full sequence, and the other one's just talking about tails of the sequence, so it's not immediately obvious as to how the two can interact. So let's apply the examples method to try and understand what's going on. In the examples method, we look at an example, we try and broaden the scope of that example, and we try and discern what's going on from looking at those examples. So let's draw an example of a convergent sequence. Here we have a sequence moving up to a limit. This sequence is bounded, as you can see by the top and the bottom dotted lines. Every term in the sequence occurs between those two extreme lines. So this sequence, this convergent sequence, is bounded. Are they all? Well, let's try altering this example and seeing what we learn. So we can push some terms at the beginning outside of the bounds, but we're always going to have to return to the limit later on because the sequence is convergent. Now that's the idea we're trying to find behind this theorem, that towards the end of the sequence we have to return to the limit, and before we can just push the bounds apart to include the noise that we've included earlier. So let's turn that idea into a proof. Now I'm not going to go through this proof in detail. If you want an annotated version of this proof, it's available in the written resource on this topic. I'm just going to point out that in this proof, as I've advised before, it's written using words and sentences, and everything I've defined, every symbol I've created for this proof has been clearly defined in this proof, which will make it a lot easier for someone to read it. As I mentioned before, there's a video about the syntactic method, which is applied to the same theorem, so if you're interested in how that method works, do check out that video. And there's a written resource that's available on this very topic. Thank you.